Hello and welcome to the last video which supports microeconomics for business and its mathematical skills. Today we are going to talk about differentiation and the use of differentiation in microeconomics. During this video I will remind you of the gradient of a straight line, and then from there we're going to talk about what is differentiation. Then I'll introduce you to the basic rules of differentiation. We're going to do quite a few practice questions so you become familiar with this concept and calculation of differentiation. Then we're looking at the applications in microeconomics. We're going to look at marginal quantities, and we're going to spend quite some time on the perfect competition. So let's start with the gradient of a straight line. We already talked about it in a previous video when we talked about the graphs, especially the linear graphs. So this concept should be somewhat familiar. So what was the rate of change? Well, remember that we were talking about the gradient being the change in y over the change in x, which we could have calculated by y2 minus y1 over x2 minus x1, where these are the coordinates of two different points on the straight line. And this concept could tell us the slope, which was the steepness of the graph. But that's exactly the same as how fast something is changing. So let's look at a couple of special cases. I have got a constant function here. Constant means it has got the same value at every single x point, so it's constant, it's the same. But that name kind of gives it away. Constant doesn't change. So the rate of change of a constant function is 0. So a constant function's m is going to be 0, simply because if you think about any 2 points on this graph, I can pick out point 1 and point 2. This is the x1 coordinate, this is the x2 coordinate, but look at the coordinate, the y coordinate is the same for both of them. So this difference of y2 minus y1 is 0. So 0 divided by anything will always going to give me 0. So the constant functions, which you intuitively sort of see that it's a non-changing function, mathematically or algebraically you can also see that the rate of change here is 0. How about the linear graph? So if you look at a linear graph, that would look something like this. So the rate of change here again, I've got point 1 and I've got point 2, and I have got the corresponding coordinates. This is x1, this is x2, and that is y1, and that is y2. So there is some kind of change in here, because I can actually visually show you that this would be the delta x, that's the x2 minus x1, and this would be the delta y, which is the y2 minus y1 distance. And basically the rate of change is how far I'm going up on the graph. So for a linear graph, as we established in the previous video, the rate of change is the same, doesn't matter which 2 points I'm looking at. So why is this actually good for us? Well, this is good for us because we can extend it to non-linear graphs. So if I have got a curvy graph or curved graph, something like this, well, I can intuitively see that this graph changes differently at different points. So let's say I'm picking up a point. This would be point P. So what is the change at this point? Well, we know how to calculate the change for linear graphs, and we know that every curve looks linear if we look at it close enough. So using those two intuitions, well, I can say, okay, I can choose a point close enough to P, let's say here, call it P prime. And if I join these 2 points, then I have got a line. And that line I can calculate the gradient of, and that would be close enough to the change, but not exactly. So what happens if I start to bring this P prime point closer and closer to the original P point? So let's say I would choose this point here, P double prime. Well, if I look at this here, it's a lot more closer approximation to the curve than the previous was. So the rate of change of this line is much better description for the rate of change of the curve than the blue one. But I can take it to the extreme. I can bring that P prime to as close to P as it's literally the same point. But what happens to that line there? Now that line that is a chord at the moment will become the tangent. And for every point on any curve, I only have got one tangent. I mean, I can have many different chords depending on which other points I'm choosing, but I can only have one tangent. And a tangent is a straight line which touches the curve only at one point, nowhere else, just one point. And that is very useful for us because then I can calculate the change of this tangent, and that will describe me the change of the function at this particular point. So I got a concept now to describe the change at one point. But what happens if I look at a different point? Let's say pick Q here. Well, I can go through the exact same thought process. I can pick a point here. I can say, well, that's Q prime, describing the change. But I can bring it closer, Q double prime, and that will be again a better approximation. But the best of it to describe the change at Q will be the tangent at Q. So again, we can see that the 2 points P and Q are at very different stages of the curve, therefore the rate of change will be very different. But using the gradient of the tangent, we can always describe the change at that particular point. So now we know the change at one point, but that's not really helping us because we want the change to trace it across the whole graph. So going through every single point and calculating the gradient of the tangent at every single point can be quite daunting. Therefore, mathematicians over the years developed a technique called differentiation. And for those differentiations, you just need to remember a few simple rules and you will be able to find the rate of change or the change function, the derivative function, for any possible functions.